Hey guys, I said that I would start off with our problem solving session by recording this video ahead of time so that you can get understanding of significant figures and how to use them in calculations so we're ready to go with some problems next time we meet. So what I'm going to do with this video is start off with significant figures. We've already introduced them, so I'll wrap that up, that introduction. I'll just sort of wrap it up a little bit. Then I'll introduce some of the tasks that we need to do with significant figures. And then I think at the end of the video, I'll also do an explanation of metric prefix modifiers and multipliers, and then use some of that stuff in calculation so that we can reinforce the idea of significant figures. So this is going to be a pretty extensive video, and I'm going to throw some practice problems in there. I might stop and start the recording as I sort those problems out, so I apologize in advance for anything that's sort of jerky or that changes really quickly. So let's get into it. Let me start up my iPad and we'll go from there. Sorry about the delay. All right. Okay. So at this point, we're back at the whiteboard, and so let's remind ourselves exactly what's involved with significant figures and what we need to do in order to sort those things out. So let's take a look here. Here's what we said. We said that significant figures tell us something about the precision of a measurement. They don't tell us anything about the accuracy. So when in scientific calculations, we use significant figures to relate information about precision. And now this isn't done in all scientific calculations. Physicists typically use will actually tell you where the error is. In chemistry, you typically assume it from the significant figures reported. And so let's take a look. What do I mean by that? And again, let's just assume that you have a scale that works, that has digits, and the digits are in ounces. Let's say one scale will read 1 digit. Another scale might read 2 digits. Another scale might read 3 digits. And yet another scale might have 4 digits. So in general, and this is a very over broad generalization. In general, when we see a measurement, the more digits that are reported, the more precise that measurement is compared to one with less digits reported. So that's where we're going real quick. And so what do we have to do? What are our goals for this video? We want to be able to identify the number of significant digits. We want to be able to make measurements with the correct number of significant figures, we want to be able to use sig figs in calculations. And there's going to be three situations that we have to work with when it comes to calculations. The situation when we're doing addition and subtraction, the situation when we're doing multiplication and division, and the situation where we do combined, all types combined. Now let me add something here. This isn't quite a complete list. I want to make a little notation up here. When we identify the number of significant figures, another thing you want to be able to do is round. And rounding is something that introductory chemistry students sometimes get a little bit confused with. I've got an example we'll talk about in just a second. So let's go from there, and let's start off with identifying the number of significant figures. Well, to be honest, there's really no problems with identifying significant figures, significant digits, unless you're thinking about a zero. And the reason is that all non-zero numbers that are reported they are significant. So ultimately what I'm going to do is I'm going to give you a number, and I want you to tell me how many significant digits are represented in that number. We're going to assume that it's a measurement. You're going to have to identify the individual numbers that make up the value presented, and one of the things that you're going to say to yourself is, okay, if it's not a zero, I count it. And so that really does eliminate, out of the 10 possible numbers, that eliminates 9 of them. The only thing that you have to deal with as a student is to figure out whether or not a zero is significant. And so let's figure out where we might find zeros in a number. And I think if we were to examine the situation and think about the possible numbers that we've seen, we realize that there are some situations where zeros might appear. There's 3 situations. The first situation is a sandwich zero. If I'm thinking about a sandwich zero, this would be a zero that appears somewhere in between other non-zero numbers. 808, 14,702. These zeros that are sandwiched between non-zero numbers, this is what I mean by a sandwiched zero. Now, remember, all non-zero numbers that are reported are significant. And so the only time you get confused about whether or not a number is significant is if it's a zero. Sandwich zeros are one of the easier zeros to deal with because sandwich zeros are always significant. And I realize I spelled this wrong. Like I told you before, I'm definitely going to be embarrassing myself on the internet by spelling things wrong. That's my shtick. Always significant for the sandwich zero. Sorry about the pause there. So anytime you see a zero that appears between non-zero numbers, it's significant. This is going to be true even if the number is, or the zero is after the decimal place. So 0.702, 12,463.031. These zeros, this zero here and this zero here, are sandwiched. And so they are significant. And so you're going to count them when we're dealing with how many significant digits does something have. Okay, so that's one situation where zeros occur that is easy to deal with. Another situation where zeros occur that is also easy to deal with are what I call leading zeros. And you almost, the only time that you ever see zeros in front are in situations like this, 0.123 or 0.00757 or 0.932 or 0.00003108. So let's think about these numbers here. Okay, leading zeros are so sandwich zeros were easy to deal with because they're always significant. Leading zeros are easy to deal with because they're never significant. And so let's take a look again. What do we got? This zero is just I call it a placeholder zero. It's just there to actually just make the number look good because we have a hesitation to write down numbers smaller than 1 without the leading zero in front of the decimal place. But 0.375 is just fine, and so is 0.375. So this is a leading zero. These are not significant. This zero here is a leading zero. It's not significant. The same thing with this zero here and this zero here. They're leading and they're not significant. But what about these guys? Well, these zeros are still considered to be leading because they appear before you get to any non-zero number. So it doesn't matter whether it's before the decimal place or after the decimal place, as long as it appears before any non-zero number, then it is not significant. It's a leading zero. Well, I just want to identify this one. What's this one? We've already talked about that. That's a sandwiched zero, so it's not significant. Or excuse me, I spoke wrong. It is significant. Remember, sandwiched zeros are always significant. All right, so those are 2 of the 3 situations. Those are the easy situations. So the sandwich zero is always significant. The leading zero is never significant. Well, if you've got sandwich zeros and leading zeros, where are the other places that you might find a zero? Another place that you might find a zero is a trailing zero. Here's where all the trouble starts. So let's review. Up to this point, what we've done is we've talked about zeros that are sandwiched, zeros that are trailing, and zeros that are leading. In the sandwiched and leading situation, it's really straightforward. In the sandwich case, they come between 2 non-zero numbers. In the leading zeros, they come before any non-zero numbers. The trailing zero situation is the one where we get all the trouble because it's got different versions of what could a trailing zero be. And so let's get some of those possibilities in play. So let's take a look. There are essentially two situations. There's a trailing zero, and there are trailing zeros. I can combine the two values to sort of show another situation like this. And so we can examine all of these situations. Now let's start off on the right with 0.750. We've already decided that the zero in front is a leading zero, so it's not significant, right? It comes before any non-zero numbers. Now the zeros at the end aren't sandwiched because they come after non-zero numbers, but there's no other non-zero numbers after the zeros at the end. So what about these two guys over here that are at zero, these red zeros in 0.7500? In this case, these particular trailing zeros are significant. And the reason that they're significant is because they don't actually need to be there. And I know that's sort of a weird thought to have, but bear with me for just 1 second. I could have written the number like this. It's the same number as 0.7500. So why would I go through the bother of writing down additional zeros if I don't need to? Well, if I don't need, the reason is because those numbers are important. At the end of the day, what's happening here is that these trailing zeros that are in red represent the precision of the instrument that yielded this measurement. And so let's go back to that example that we started with the scale. This one is obviously the scale that has three total digits. This is the scale that had 4 total digits. If you have a kitchen scale that has 4 total digits, these things just don't blank out if they're actually 0. They show the 0 because what the scale is saying to you is that I know what the measurement of the mass of this, whatever it is you're weighing, is. So if I have all 4 of these decimal places, what could it be? It could have read 0.7499. It could have read, and I'm going to add the 2 digits on this side just so I have some room, 0.7501. It didn't read either of those two. It read this one. So what that means is that the scale is precise in the sense that it knows that or it thinks, or it's decided. Remember, it doesn't say anything about the accuracy. Its measurement reads 0.7500, not 0.7499, not 0.7501, but 0.7500. So those particular types of trailing zeros, they're significant. And so let's go back to the other side and let's take a look at 1200. What about 1200? What about these zeros? Well, I'm gonna mix up things a little bit, and I'm gonna talk about it in the same way that I talked about the other trailing zeros. The trailing zeros in red, we said, are significant because we don't need them, right? Because the number 0.75 doesn't change if I have zeros or I don't have zeros at the end. 0.75 is the same value as 0.7500. Using that same idea, the trailing zeros in 1200, I do need them, right? Because if I don't have the trailing zeros in 1200, what do I have? I get 12. And you would know, I hope, that 1200 is not the same as 12. 12 is not the same as 1200. So I need the zeros. I need the zeros to represent the value. So that means that they're not significant. So if I have these trailing zeros and they're just holding the place to represent value, then I don't really need them and count them as significant. But that's really an oversimplification. So the truth is that the word that we use is it's ambiguous. In other words, what we're saying is that the 1200, it may or may not be significant. We don't know. The author or the person who wrote down this measurement didn't indicate in any way where the significant digits are. And so with a number like 1200, the technical answer is that it's ambiguous. But the reason I started off by saying they're not significant is because that's the assumption that you have to make when they're ambiguous. We assume they're not, because if we assume they are, and it turns out that they're not, then we're adding precision that isn't there. And we want to represent, typically we're representing the worst case scenario. And so if we're telling a reader about a measurement or a calculation we did, and we're reporting that, we want to report that with the best possible precision that we can, that we know about. But if there are uncertainties, then we'll make the worst case assumption. And so if it's ambiguous, we assume that they are not significant. The truth of the matter is we don't know unless the author does something to represent whether or not those zeros are significant. So what are some things the author could have done to represent these digits as significant? To say that the measuring device actually knows that it's 1200 and not 1199 or 1201. What the author could have done is the author could have added a decimal place just right there and said, ha, there's the decimal. And now I'm telling the reader that these particular zeros are significant because I know the measurement to that level of precision. Another common method is to use a line. Just the same in math, we use that line to signify repeating values. In chemistry, we can use the line to represent where the significant digit is. And so we could say that if we put the line there, then we're saying that that zero with the line is significant. And then that means the other zero becomes sandwiched, so it's also significant. If we put the line here, then we know that the zero on the right of the line is just there for holding places. It's no longer ambiguous. It's definitely not significant. But the zero with the line is. And so in this case, there's 3 significant digits. And so let's take a look. What about 1200.7500? Well, these zeros that are to the left of the decimal place, they're no longer trailing. In this example, I've just switched them up from being trailing to being sandwiched, so they're significant. These zeros are at the end, so they're still now they are trailing, but remember they don't need to be there because 1200.75 is the same value as 1200.7500. So then these must be representing the precision of the measurement, and so that means they are significant. So this one has 1, 2, 3, 4, 5, 6, 7, 8 sig figs. And so now you should be able to take essentially any, one other thing I could have done with 1200. One other thing I could have done here to represent that how many significant digits there are is I could have written the number in scientific notation. In scientific notation, we include all of the significant digits. And so what I'm doing essentially is taking ambiguous zeros and making them into trailing zeros that I don't need to represent the value. I've got 1.2 times 10 to the third. I don't need the zeros in order to have 1.2 times 10 to the third. The zeros now 1.200 times 10 to the third are telling me that these two zeros are significant because I've included them in the scientific notation. So anytime you see zeros in scientific notation, you know for a fact, boom, they're significant, because if I didn't need them in the scientific notation, if I didn't need to signify that level of precision, then I wouldn't have included them. And so let's just do a couple of quick little examples. So let me write down a few numbers and we can go let's count the number of significant figures. And so I'll go through these. I'll go through them pretty quickly because you can rewind and you can take a look at it. If you're confused, you can go back. All right, so let's take a look at 42.43. Remember, if it's a non-zero number, it's significant, and all the numbers in 42.43 are non-zero. So this one has 4 sig figs. What about 7,200? What kind of zeros are they? They're trailing zeros. I need the trailing zeros to represent the value as 7,200 instead of 72. So these digits are not significant. In other words, they're ambiguous because the author, me, didn't show you whether or not they're significant. So I assume they're not. And I say that one has 2 sig figs. What about 15,703? Well, remember, all the non-zero numbers are significant. So 1, 5, 7, and 3 are significant. That's a total of 4. Well, what about the 0? Is it significant? What kind of 0 is it? It's a sandwiched 0. So it is significant, right? Sandwiched zeros are always significant. So that one has 5 sig figs. All right, what about 9.320 times 10 to the negative 6? Well, what do you notice about that number? It's in scientific notation. The 0 in the scientific notation is trailing. I don't need it to represent the value 9.32. It's there to, that 0 is there to represent the precision. Since it's in scientific notation, I definitely count it. So this one has 4 sig figs. Well, what about this number? 0.000300256. So again, what about these zeros here? They're leading. I don't ever count leading zeros. So none of these zeros in brown count. But this other 0 between the 3 and the 2, it's sandwiched, so it counts. So I get 1, 2, 3, 4, 5 sig figs here. Okay, so I hope with that you have some idea about how to count the number of significant figures. And so what I want to do now is I want to talk about how do I report these significant figures correctly in a measurement. And so I'm actually doing 2 things at the same time. I'm showing you how to use an analog measuring instrument, because if it's digital, right, and it just has digital digits, you just write down all the digits that the instrument shows. If the scale says 12.75 ounces, then you write down 12.75. What do you do with an analog? What about one of these analog instruments? So with an analog instrument, you have to read between the lines, and that's not a metaphor. It's what you really have to do. take a look at where the thermometer's red liquid that indicates the temperature actually is. And I'm using this blown up picture so that we can actually do a little bit of detailed examination. Here are the lines, that one and that one, but look what I have in between. I have this line, this line, this line, and this line. So what do? If I start right here, what's this line represent? That's 80. What does this line represent? 90. So what's each mark in between? This one must be 85. So that each mark in between must be 1. So this is 81, 82, 83, and 84, respectively. My ink's a little thick, so I'm not going to fill them all in. Okay, and so let me back off those. I want to get back to my clean thermometer. And what do I want to point out? I want to point out that the top of this line clearly falls in between two of the lines. What lines do they fall in between? This one and this one. So what was that? That's 85, 86, that's 87. And it falls in between 87 and 88. So how do I report the correct number of significant digits to represent the actual precision of this instrument? And so I'm showing you how these things are related. Well, when we use an analog instrument, each line is called a graduation. So the graduation of this particular instrument is every 1 unit, 1 degree, if it's a thermometer. So where's the precision lie? The precision lies in between the smallest graduation. Why? Because you can use your eyeballs and you can see that it's the value is not 87, it's not 88, it's in between, right? So I can visually, with my mind's eye, I can, let's see what I can do here. I can cut with my mind's eye and add, and it's much harder, it's hard to do because of my, let's see if I can zoom in just a little bit. I don't want to get too crazy here. I can make visual or imaginary graduations with my mind's eye. So how does that work then? So what do I actually report? You report 1 digit with more precision than the smallest graduation. If the smallest graduation is in the ones place, then I need to report this digit. I need to report that digit. So what's the actual measurement then? Well, it's in between 87 and 88. It's about halfway in between, so it's 87.5. That's how I use one of these instruments. Let's take a look at another ruler here. This one's a little bit more clear. The resolution is just a little better. And so let's take a look at that guy. I got inches on one side, millimeters on the other. And so this one, actually, the inches one, I'm not going to talk about because its graduations are actually in fractions, right? So if I talk about inches, then this is all the way over here is 0. And this is 1 inch. And so this one must be a 1/2 inch. And so then this one is a 1/4 inch. This one is 0.75 inches. We typically deal with the metric system. And so all of our graduations are in units of 10. And we're going to see that here at the bottom of the ruler because it's in millimeters. And so what we're saying is that the lesson for the reporting the graduations isn't really appropriate to an English ruler. If these graduations are actually 1/16 of an inch, and so between them, excuse me, they're not 1/16, they're 1/32. So in between would actually be 1/64. And I wrote 36, not 32nd. So 1/32. So it's 1/64 is in between. Now, when we're doing construction work, when we use inches, the tolerances, we don't need that kind of precision. So let's take a look at the metric version of this ruler where it looks like millimeters. So here's millimeters. What does the millimeter mean? Does that mean that this is 1 millimeter and that's 2 millimeters? Is this 1 millimeter and this 2 millimeters? No. What it's saying is that the smallest graduation is a millimeter. And we're going to get into metric prefixes here in a second, but at the end of the day, the smaller graduations are millimeters, so that means that the larger graduations are centimeters. And in a little while, I'm going to teach you how to convert between millimeters and centimeters, and you'll see that these things are related by an order of 1 magnitude, 10 to the first. Okay, and so how would I read this device though? So I know let's put a fake piece of material. So I'll draw in my fake piece of material and I want to measure its length. Okay. So where do I see? What do I see? I see that it falls somewhere between 1 centimeter and 2 centimeter. So I know that it's 1 centimeter with some change. So what kind of change do I need? Well, the smallest graduations are 0.1 centimeter. But what was the rule? The rule is we read an analog instrument 1 decimal place beyond the smallest graduation. If this is the smallest graduation, then we need to fill in 1 extra decimal place. So what digit belongs in the box labeled A, and what digit belongs in the box labeled B? Well, A is whatever is between here and here. And so let's take a look. It's 1.1. I'll expand this out so you can see it a little better. 1.1, 1.2, 3, 1.4. There's 1.5. This is 1.6, and that's 1.7. So it's in between 1.6 and 1.7. So we know that it's 1.6, but it's more than that. Well, so then look in between, use your mind's eye to do an additional set of graduations. How far beyond 1.6 is it? Well, it's more than halfway. Where would halfway be? Halfway is kind of there. So that would be 1.65. So what is it? Is it 1.67? Is it 1.68? Is it 1.69? It's uncertain exactly which one it is. Pick one, right? This is the whole point of the representation of the precision of the instrument. Do your best to pick the number that it is. I'm going to go with 0.68. Where's the uncertain digit? The uncertain digit is the last one. This one has the least certainty. We know that it's 1. It isn't 2 centimeters. We know that it's 0.6, so it's 1.6. It's not 1.7 because 1.7 is right here, and we haven't got there yet. So how many significant digits does this instrument deliver? It delivers 3 significant digits in the range that we're talking about. How many decimal places does it deliver? 2, right? Because the smallest graduation is that decimal place. So we need 1 more decimal place to get the correct precision of the instrument. There's one more example with analog instruments, and it's this one. And so I just want to make sure, it's a little too thick. I just want to make absolutely clear what we're looking at here. We're looking at this measurement, boom, it's landed right on the line. So let's take a look at the graduations. It looks like it's every 30, it looks like it's every 1. So this is 30, 31, this one would be 35, 36, 37. This one is 38. And so let me make my pencil a little smaller. This one is 38. So how do I report this correctly though? Well, remember, I always report 1 decimal place beyond the smallest graduation. And this is true even if it lands, bam, you've decided, boom, it's right on it's on the line. There's no ifs, ands, or buts about it. The measurement is on the line. So then what do I do now? Well, I still want to report the value to 1 extra decimal place. And so I don't report 38, I report 38.0. And so this goes all the way back to this conversation we were having about trailing zeros. Why do we need that trailing 0? Because 38 and 38.0, they're the same number from the mathematical perspective of its value. Why do I have the 0 then at 38.0? To represent the precision of the instrument. Because what I'm telling the reader is that the temperature that I measured, I did that on an instrument that is precise enough for me to say to you, it's not 37.8. It's not 38.2. I know that it's right on the line. It's 38.0. So that's how we do that. And that's really the conclusion of how do we count sig figs, how do we report sig figs from analog instruments, and how do we read analog instruments. Okay, that's the easy part. That is definitely the easy part. Now comes the hard part, and the hard part is using sig figs in calculations. This becomes a challenge. Multiplication and division is pretty easy. Addition and subtraction is a little bit more difficult. But what's hard for students is using sig figs in calculations where the operations addition and subtraction are mixed up with multiplication and division. And so let's take a look. Let's do the basic rules. Let's start off with the easy one, and that's multiplication and division. So the reason that it gets to be a challenge is there's actually 2 different sets of rules with dealing with significant figures and calculations. Multiplication and division, the rule is this: you report your answer using the least number of sig figs from any value in the calculation. And so this is going to be the first sort of example of how this course is going to build on itself. It's not like another course, and I'm going to pick on history because my colleagues love me to pick on history. But you can learn about World War II and then learn about World War I, and you can really learn about them separately. So if you're in the course and it's the history of the world wars, then if you totally forget about World War I, you're not really going to miss anything with World War II. Maybe there's some connections politically, but you see what I'm trying to say. The facts behind World War I aren't really related to the facts in World War II. In this course, all the skills that you develop early on, you need to use them later. And so this is going to be the first example. And so report your answer using the least number of sig figs from any value in the calculation. Well, how does that relate to what you just learned? You have to know how many sig figs are in the number that you're using in the calculation. So that means you have to be able to identify the number of sig figs. And so let's give it a try. What about 23.76 times 15.9? So I made it easy in this case because there's no zeros. And so the number on the left has 4 significant digits. The number on the right has 3. So when I put this into my calculator, 23.76 times 15.9, my calculator spits out 377.784. Man, my calculator's dumb. It doesn't know anything about significant digits, does it? And that's the thing. Your calculator is good at doing mathematical operations, but it doesn't have any clue about significant digits. And I have yet to see a calculator that can round to significant digits. And so now that we've got multiplication and division in the game, and we're using significant digits in calculations, we have to round. All right. And so how many significant digits should I report my answer to? Remember, this is the calculator. What am I going to report? All right. I'm going to report 3 significant digits because the number that I used in the calculation has the least value of sig figs is the one with 3. It's 4 versus 3, so 3 is the one that I use. So how do I deal with 3 sig figs? Well, I'm going to count. 1, 2, 3. So there's 3 significant digits. So what do I report? 377? Take a look at this digit. It's more than 5, right? And so what does that mean I need to do with the 7 in the ones place? I need to round it up. 378 is what I'll report. Now, there's some texts talk about whether or not it's even, whether or not it's odd, whatever. If it's 5 or more, round up. If it's less than 5, round down. And there's some statistical analysis you can talk about of how that introduces a slight bit of error. At the introductory chemistry level, that's not poo on that. I'll argue with my colleagues all across the country about whether or not that's actually teaching you anything. So I digress. So what am I going to report? I'm going to report a number that has 3 significant digits, 378. And I rounded the 7 to an 8 because the number after the 7 is also a 7. That's larger than, that's 5 or more. So I'm going to round up. If it's less than 5, I just get rid of it. All right, so what do we got? Let's take a look at 3,075 times 293.62. So what do I get? 3075 times 293.62. My calculator spits out 902,881.5. Well, how many significant digits do I need to use? How many does the one on the right have? The one on the right has no zeros, so it's clearly 5. The one on the left has a 0, so I have to sort that out. It's a sandwich 0, makes it easy. That's significant. So this one is 4. So I'm going to report my number to 4 significant digits. So where's the 4th significant digit? 902. So this is 1, 2, 3, 4. There's the 4th significant digit. What do? It's an 8. The number after it is an 8, so I need to round up. So it's 902,900. That's okay as far as reporting your value, and that's, in my class, that's a correct answer. But what have I done? Let's go back to this idea about zeros and significant figures. These are trailing zeros, and I absolutely need them to keep the value, right? Because without the zeros, it goes from 902,900 to 9,029, and that's not the same number at all. So I clearly need them. So that means that they're not significant, but I didn't actually say anything to the reader to indicate whether or not they're actually significant, and that means that they're ambiguous. So what can I do? What can I do to tell the reader? Well, I can use a little line right here and say, there's the last significant digit, right? So now there's no worries about it. It's clearly 4 sig figs. The zeros are just there to hold places. And I use the line to do that. What's another way? The other way is scientific notation. I could have turned this into scientific notation. So here's where my decimal place is. 1, 2, 3, 4, 5. So the value is 9.029. There's all 4 of my significant digits times 10 to the 5th. And that takes all the ambiguity out of it. Now I know it's exactly 4 significant digits. I don't have to worry about it. So the same thing goes with division. If we're doing something with division, then I can divide, and I'll just use numbers that have scientific notation. Let's use that 9.29 times 10 to the 5th. Let's divide it by 1.738275 times 10 to the negative 3. Okay, and so you can just enter in these the numbers in scientific notation in your calculator. If you have some problems with using your calculator in scientific notation, let me know, and I'll give you some help with that. 1.73825 times 10 to the negative 3. Whoa, what does my calculator spit out at me? My calculator spits out this huge number, 519422991.184. How many sig figs do I need to report? Well, the bottom number doesn't have any zeros, so it's 1, 2, 3, 4, 5, 6, 7. The one at the top has a sandwich 0. It counts, so it's got 4. So I need to report 4 significant digits. I'm in the same boat as I was before. 1, 2, 3, 4. In this case, the number after the 4 is a 2, so I don't round up. I just truncate it off. So the value is 519,400,000. And remember, these are now ambiguous, so it might be best to say 5.194 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. Okay, let's do addition and subtraction. So addition and subtraction is a little bit more of a challenge. With addition and subtraction, what we do is we have a different rule. And the rule is not, I repeat, it is not the least number of significant digits. The rule is report your answer using the same number of decimal places as the value in the calculation that has the least number of decimal places. So this is a little bit different. Instead of counting sig figs, we're now counting decimal places. So let me make sure that we're getting this straight, right? In order to use addition and subtraction and report your answers with the correct number of significant figures, we count decimal places. And this is a completely different rule than multiplication and division. In multiplication and division, we are counting the number of significant figures. In addition and subtraction, we're not. We're counting the number of decimal places. And so let me give you a quick example. If I have 25.32 plus 0.11, how do I report my answer? How many decimal places does the number on the left have? The number on the left has 2 decimal places. How many decimal places does the number on the right have? The number on the right also has 2 decimal places. So my answer should be reported to 2 decimal places. So the answer would be 25.43. So this can actually get you into some weirdness, right? And so let me show you what I mean by that. What if I did this? What if I had this value? If I said, we want to do a calculation and I want to make sure to report it to the correct number of significant figures. So instead of 25.32, it's 2,532 plus 0.43. Okay. If I put this into my calculator spits out 2532.43. So what's the rule though? I'm counting the number of decimal places. 0.43 has 2 decimal places. Well, how many decimal places does 2,532 have? The way it's written has no decimal places, 0. So I need to report 0 decimal places. So here is the ones place. That's the last digit that I'll report. So I want to look over here. It's a 4. It's not a 5 or larger, so I'm not going to round it. So what do I report? 25.32. So there's the weirdness that I was talking about. Yeah, what we're saying is that at the level of precision of these 2 measurements, when I add 0.43 to 2532, the answer is 2532 because we want to represent the correct level of precision. In the math class, this is it. We stop here. In the chemistry class, we're saying that they're not just arbitrary numbers, they're actually measurements. And when I add measurements or do calculations with measurements, I don't want to add artificial levels of precision. When I report my final answer, I use these rules in order to avoid that. And so if I did a calculation like this, the answer turns out it's just the same as the 2532 because of how I applied the rule. If I do one other quick example, 173.72 minus
102.135. What do I get there? If I put that into my calculator, 107.72 minus 102.135, I get 5.585. This one has 2 decimal places. This one has 3. So I want to report to 2. That's this one here. So my answer that I report will be 5.59, rounding up because that's a 5. Okay, so we're almost there. We're to the home stretch here. And so now we're getting to the hard part. The hard part is here. What if I have combined operations? Yeah, this is really where it gets stressed out. What if I have multiplication and division combined with addition and subtraction? And let me show you what I mean. It would be complicated like this. 25.9.79 minus 3.1 divided by 1.27 times 32. So what do we have going on? In the numerator, in the parentheses, there is a subtraction. In the denominator, in the parentheses, there's a multiplication. And then at the end, I have to do a division. And so remember, you're going to use the same order of operations that you use in math, right? Please excuse my dear Aunt Sally. Parentheses, exponents, excuse my multiplication, dear, division, Aunt Sally, addition and subtraction. And so you have to still process the calculation correctly, right? You can't just add, you can't just do the steps wrong, right? You can't take 3.1 divided by 32 and then subtract the answer from 25.79 and then divide that by 1.27. You'll get the wrong answer. So remember, you still have to do the order of operations. So what is the rule when you have this combination of calculation types? The rule is this. You have to stop and apply the respective addition or subtraction rule, but you don't round. So this is where it gets hard because you have to keep track of significant digits, but not round until the very end. And so let me show this in process. So let's do the top. I'm not going to do anything with the bottom right now because I'm not changing that. But let's do 25.79 minus 3.1. And this is okay to continue to just write what your calculator has. 22.69. But what's the rule here? The rule is we're doing subtraction. So I need to do the addition subtraction rule, which is count decimal places. 3.1 has 1 decimal place. 25.79 has 2 decimal places. And so we use the 1 decimal place, but we don't round yet. So this is where the hard part comes in. Not only do we have to process these rules one at a time, we don't round until the very end. And so that means we have to keep track of the number of significant digits because we don't want to introduce rounding errors into the calculation. So that means I need to do something. And I'll just use this line because this is the same line I've been using before to indicate where the last significant digit is. So what I'm telling myself when I do this, I'm keeping track of this, is that 22.69 is the value that I need to put into my calculator, but the 6 is the last significant digit, not the 9. So the number now in the numerator has 3 significant digits, not 4. But I don't want to round off that 9 and report 22.7 just yet because that introduces rounding error. So now let's go ahead and process the denominator. 1.27 times 32. So what do I get there? And I'm going to leave the numerator the same because I'm not doing anything with it yet. It's 22.69, but I want to go ahead and remind myself that the 6 is the significant digit. And so my calculator gives me 40.64. And so what's the rule here? It's multiplication and division, and so I use the least number of significant figures. So the least number of significant figures is 2. 32 has 2, 1.27 has 3, so I have 2. And so where's the last sig fig? Well, in this case, in 40.64, if this number is the second significant digit, then I would normally round it to 41. But I don't do that yet. Remember, I'm not rounding until the end. So I'm just keeping track of the number of significant figures with the line. Okay, and so let's do the last step of the calculation. 22.69, using all the digits so I don't introduce error, divided by 40.64. My calculator spits out a crazy long number. 0.558316929113. I got a nice calculator. It goes way far out. Okay, but let's keep track of the sig figs. Well, what did I do? I did a division. So the rule is the least number of sig figs. How many sig figs in the numerator? 3. How many sig figs in the denominator? 2. I know that because I kept track along the way and I made a mark so that I could do that. So that means I report my answer, my final answer, to 2 sig figs. And now's the time to round. Now I can round. 0.558, I round up. 0.56 is what I report. Now, sometimes if you round in between, you're going to get the same answer. You're not going to introduce any rounding errors. But sometimes, like maybe on an exam or a quiz, if you don't, you will introduce a rounding error. And so the choice that you make will be wrong. And that's one way I can test you to see if you know the rules, is by designing a problem that if you round in between, you do get a different answer. And that way I can tell, oh, Billy didn't know the rules. He rounded at every step. That's why he got this weird answer. Now I can address the problem with Billy. But when we're doing practice, make sure that you're not rounding until the very end. Okay, that concludes significant figures. And so at this point, you're starting to get a little bit frustrated, a little bit sweaty, because that's a lot of information. And remember, what we're going to do the next time we meet is practice with these sig figs. And so what I want to do now is I want to do one last little bit, and I want to introduce some definitions. And these are just going to be definitions, and they're definitions for metric prefixes. When we talked about the SI base units, the unit for mass is the kilogram. And I said it's the only one that has a prefix multiplier associated with it. The K, kilo. And so that's what I mean by metric prefixes and prefix multipliers. What we need to do, and we're going to use them in calculations later, is we need to take those metric prefixes and prefix multipliers, and you have to just memorize them. And so what I'm going to do right now is I'm going to write them all down so that you know which ones you have to memorize. And then I'm going to show you how to write an equality, and an equality is something that uses an equal sign. So how to write a correct equality. And what I mean by that is this. If I want to make kilograms equal to some number of grams, how do I do that so that I'm right and not wrong? Now, some of you may know that 1,000 grams is a kilogram, and that's great. We can do that all day long, and that's correct. I'm going to actually show you a way based on the definition, and I'm going to use it systematically every time, because in order to avoid memorizing all these different conversions, all you have to do is memorize the definitions, and you memorize them in an order of magnitude. And then we use those orders of magnitudes in these conversions, in these equalities, and we use them the same way every time. That way it's very consistent and very repetitive, and we're not introducing any new things. Certainly it's true that 1 kilogram is 1,000 grams. Certainly it's true that 0.001 kilograms equals 1 gram. Those are true. But I'm going to show you the way to do this with the definitions. But let's do the definitions first. Okay, so I want to start off with a base unit. And in this case, because we've been doing it, I'm just going to start off with the unit gram. Remember, it could be seconds, it could be moles, it could be kelvins, whatever it is. It's any of the units, and we're just going to add a prefix multiplier. Here's the order of magnitude, and I'm going to start with 10 to the 0 because 10 to the 0 represents the value of 1, right? So if I take some value of grams, multiply it by 1, it's the same number. Okay, and so let's take a look at the prefixed units then. I'm going to go up, getting larger, and then I'm going to go down, getting smaller. And so we've already talked about the next one up, the kilogram, and it's kilo. And the symbol is K. What's the definition of kilo? The definition is 10 to the third. And so what I'm actually going to do is I'm going to move these out of the way because I want to put these together. Kilo with the symbol K is equal to 10 to the third. We're talking about the base unit of being grams, so I just want to put the example right there in that location. Okay. So here's the symbol. This one is the base unit. This is the name, kilo. And so let's continue to go up. So these are the ones you have to know. 10 to the 6th. This one is mega. And its symbol is big M. And so a megagram would be big M with a little g. The next one up is giga. G-I-G-A. Big G. It's 10 to the 9th. And so that would be a gigagram. There's one more after this. And I think we should go ahead and put it down. You know what? I'm going to leave it just like that. We'll leave it like that. Okay, so we went up. We got larger. So we went from 1 to 10 to the 3rd, which is 1,000, 10 to the 6th, which is 1,000,000, 10 to the 9th, which is 1,000,000,000. Let's go down. Notice that these go up in orders of 3, and we're going to do that down as well, except for the first one. 10 to the minus 2. That is centi, as in little c. And so that would be a centigram, like a centimeter, right? We can do gigameter, megameter, kilometer, meter, centimeter. In this case, we're using grams as the example. It's the only one that I want you to memorize that isn't in an exact order of 3. So the definition of centi is 10 to the minus 2. The definition of kilo is 10 to the 3rd. The definition of mega is 10 to the 6th. The definition of giga is 10 to the 9th. The next one down is milli. It's little m. It's 10 to the minus 3, so it's a milligram. Then it's micro. And I've already used all of my m's, so what I'm going to do is use a Greek letter m, mu. It's 10 to the minus 6th. So I've got a Greek symbol here for microgram. And the last one that you need to know is nano. It's little n, it's 10 to the minus 9. And so the example would be nanogram. And so these are the ones you have to know. You have to know them by heart. So, and what I'm going to do now is I'm just going to conclude with showing you a couple of examples about how to write equalities that are true and always true, because we're going to use equalities to do conversions. And at the end of the day, doing conversions is one of the most difficult parts of chemistry, especially intro chemistry. And so we got to get a good start. We got to really figure this out. And so it all starts off with equalities. And so this is the first time we want to deal with these equalities. And so an equality involves an equal sign. And what I'm trying to do is say that one thing equals another thing, and I want to be right so that when I use it in a calculation to do a conversion, I'm not introducing errors by being wrong. So how do I do this? I want to make a comparison, an equality between the base unit and some prefixed unit. What I mean by that, for example, is grams and kilograms. It's not that there isn't an equality between kilograms and micrograms. I can come up with numbers to make this true, but I'm going to avoid that because I want it systematic, and this is my systematic way. How do we do this? All right. It's all about the definitions. And remember, the definitions are these orders of magnitudes. These values are the definitions of the prefixes. So how do I do this? I've made the comparison between grams and kilograms, and I want to write the equality down, and I want it to be true. So I need to put the numbers in there correctly. This is how I do it. I use the definition. Where do I put the definition? I put the definition with the base unit. Every time I'm going to do this. Where do I put the exponential definition? I put it next to the base unit. So I write 10 to the third here with the base unit and not the prefixed unit. With the prefixed unit, I just use 1. So what I'm saying is, now that I've figured this out, this is true, right? 10 to the third grams equals 1 kilograms. And if you remember, 10 to the third is 1,000. And we wrote this one down before. This one's true. It's obvious with 10 to the third, but it becomes less obvious when you use different values, especially negative exponents. And so you want to keep track of that correctly. Let me give you an example. What if I wanted to do micrograms and grams? Well, first thing you should notice is that I put grams on the right instead of on the left. Does it matter? It doesn't, as long as I follow the rule. And the rule is this. Use the definition. I'm repeating myself. Use the definition. What's the definition? The definition of the prefixed unit. In this case, the prefixed unit is micro. What's the definition of micro? And definition is the order of magnitude. So what's the definition of micro? It's 10 to the negative 6th. Where does it go? It goes with the base unit. Now this equality is true. 1 microgram is equal to 10 to the negative 6 grams. So try to do a couple of other ones on your own. Do the relationship between grams and megagrams, and do a definition between nanograms and grams. Fill those in for yourself. Remember, the rule is, what's the definition? Where does it go? And the answer to where does it go is always with the base unit. All right, that's enough for this video. I hope you watch it. I hope you get ready to do this. We're going to do a little bit of practice. As we're going to start off, we'll probably pound it for about an hour. And that means you really need to have this video knocked out and have a basic level of understanding before you're able to approach those problems. Because the last thing you want to do is be twiddling your thumbs and wasting an hour of your time. All right, guys, have a good one.